Hey everybody, it's Wednesday morning and I'm going to go over some tips for assignment 5 to help you finish it. First of all, I attached this image to the assignment post. This is just a great review of the equations we're going to be using, and a lot of this work is choosing the correct equation for the situation and plugging in values. The information for first order rate law especially is given on the AP test. And then the other situations are just going to be used in context, not a whole lot of pulling the equations out of a bag kind of questions for zero order and second order equations. But first order, they do give you the integrated rate law, which is this concentration versus time integrated rate law is what we called it in class. But it is a concentration time equation, like a y equals mx plus b format. So we can use it to plot points, determine values given a time value, given a intercept, given concentration at some point in time. There's a lot of variety with the integrated rate law or the concentration time equation. So let's look at some examples from the homework and I'll get you started. So number 38, we're going to go ahead and read through and look for some keys as far as what kind of equation we're going to be using. We have a sub naught, which is an initial value. That little zero next to the brackets means initial at time 0. And so we have some concentration, okay. And the plot of natural log versus time is a straight line. So right away, this tells me first order. Go back and check the graphs if you need to refresh yourself on which graphs give you which order. But a straight line for a natural log versus time graph gives you first order, or confirms that as a first order reaction. And it says the slope value is given right there. So let me clear up a couple of these things. And then we need to determine the rate law, integrated rate law, and the value of the rate constant for this reaction. So A is just a formality kind of question. Once you know it's first order, and we're going to represent the reactant as just the letter A, the rate law is going to be K times the concentration of A to the first order power, or we can just get rid of that 1 because it's a 1. Here's the rate law equation. The integrated rate law is just choosing the first order equation. So it's the natural log of the concentration equals negative KT plus the natural log of the initial concentration. And I write it this format, which is slightly backwards from what's given on the table. I write in this format because this is the y equals mx plus b format. So it matches up with graphs really well. There's the integrated rate law. And then the rate constant for this reaction. The rate constant is K. Rate constant is K, which is equal to the negative of the slope value. Because when we graph the natural log of A over time, it's a negative slope, and that the opposite of that slope is going to be our K value. K values are always positive, and as long as the temperature is constant, this K value is going to stay constant. So once we establish K, as long as we maintain the same temperature, any trial after the first one is going to have the same K value. So the slope value is given in the question, and so we just take the opposite of that. And it's per minutes. So just keep in mind what the units are. All right, so there's A. Calculate the half-life for this reaction. So I'm going to go and clear this up. We need to just choose the correct equation. So go into my equation list. The half-life is the natural log of 2 over K. So all you need to know is this K value, which we're going to make positive, the slope value, which we're going to make positive. And that just goes right in there. Another plug and chug. And for C, we're going to do the substitution step. How much time is required for the concentration of A to decrease to some new concentration? And if it ever asks about time, really the only equation that uses time is going to be that integrated rate law equation as far as concentration and time. So for C, we are going to choose the we're going to just write out the integrated rate law equation again and substitute. So it gives us the initial concentration, so we're going to plug that in there. And how much time is required for the concentration A to decrease to? So the concentration at some point in time, this concentration value goes in there. So natural log of 2.5 times 10 to the negative 3 equals negative of the slope value, 2.97 times 10 to the negative 2. We have our variable which we're solving for, which is t. So I'm just going to put that in a different color for now, plus the natural log of 2 times 10 to the negative 2. So here's our substitution. Don't forget to take the natural log. Technically, you can combine the natural logs. You can subtract both sides with a natural log, divide those inside the fraction, then natural log does one number, if you're familiar with how to math out natural log. But if you just plug it in your calculator, solve for t, then you'll be fine. In this case, you don't have to break a natural, you don't have to do any weird funky rearrangement with a base e to figure out t. You just kind of plug and chug. So I'll let you finish this one. So go ahead and try this question first. I'm going to spoil the answer just so you can check your work, since this is an even numbered question. When you solve everything, you get 70.0 minutes. You want to take a look at the value for K. This is per minutes, so this answer has to be in minutes, not seconds. So just be a little careful. I know we do work with seconds a lot, but the units can vary widely. Question 40 is done pretty much the exact same way. So just a different set of data, different plot, different order. So just choose the different equations and practice substituting that in. 41, we are going to do the substitution process. You can check your work in the end of the chapter questions. So by mentioning a temperature, that's just a formality saying the temperature is 600 Kelvin, and that's going to stay 600 Kelvin. So we don't have, so our K value is going to stay constant. We do see a slope of -4 times 10 to the -5th. So the slope is -K for this particular plot. It is a concentration versus time. If it's just concentration versus time, that's saying zero order. And I fully encourage you to annotate your questions when you get them on paper in front of you. This is moles per liter seconds. So I mainly wanted to go over the substitution step for part C because A and B are, again, kind of formality questions, just choosing the right equation, plugging in half-life information. How much time for all the 1.25 times 10 to the -2 molar, how much time is required for that whole thing to decompose? So essentially this is asking, when does the reaction stop? So we're going to choose, again, we're talking about time, so I'm going to choose the integrated rate law. The concentration equals -kT plus the initial concentration. So this is a very basic y equals mx plus b. So how much time does it take for all of this to decompose? So we're starting with an initial value and our final value is actually 0. How much time does it take for everything to go away? So we're just going to plug in our slope, which is negative of 0.400 times 10 to the -5. Our t value is what we're solving for, how much time. And then we have our initial concentration, 1.25 times 10 to the -2. So I think a question like this could be a little tricky because you're trying to figure out how to substitute, and your job is to determine that it's actually asking for how much time does it take for the concentration to reach 0. And then you can rearrange and solve for t. Um, 45 presents an interesting part, just mainly because in 46 also is based off of exercise 45. So we're going to do 45 and 46 together. We have an obvious linear plot for this one, which is going to be second order based on the axes right there. So we're just identifying that as second order. And if we wanted to, we can start looking, there's points plotted there. If we need our K value, I'm just kind of thinking ahead, potential that we could do rise over run and find our K value if needed. What is the concentration of A? It's asking, what is the initial concentration? What is the order of the reaction with respect to A? And what is the initial concentration? So it looks like we actually are going to have to solve for K, because if we're trying to find the initial concentration, we're not seeing any sort of intercept on the concentration versus time graph. So we are going to have to go ahead and plug it into our second order concentration versus time equation. And the initial concentration is what we're going to be solving for. So we're going to choose a set of points from the graph, and it's laid out so it looks pretty straightforward as far as figuring out rise over run and figuring out a point on the graph. So I'm going to go ahead and zoom in and let's figure out a point on this graph. So we have a point here, which is 2 and 30. And we point here, which is 4 and 50. So I'm just going to go ahead and say 20 is the change of y over 2, which is the change in x. So the slope is about 10. Up and 4 over. So change in y over change in x is going to be our slope. And so I'm just going to choose one of these values. Let's choose 230 as our point to plug in. And so we're going to say 1 over 30 equals our slope of 10. And that value, the concentration is 30 at 2 seconds. So I'm going to plug that in for our t value. And then we can figure out our variable, the initial concentration from there. So we get all this, and we need to do an inverse of 30, get a value for that, and subtract 20 from it. So I get negative 19.97-ish. I'm just going to keep that in my calculator because let's bring the concentration over here and switch places, and we're just going to inverse this number. So the initial concentration looks like it's going to be notice the little brick wall I reached here. Notice what happens. The numbers don't really match up. This gets a weird number, it becomes negative. Something happened here. So let's back up. We got to be careful with these graphs because the data given off the graph is based off the axes, of course. And while the value on the graph is graph size. There we go. While the value on the graph looks right about there. While the value on the graph is 30, this 30 represents 1 over the concentration. So when the substitution asks for 1 over the concentration, we're going to replace this entire thing with 30. So it should be 30 equals 20 plus 1 over the concentration. So we get 10. And when we solve for the concentration and inverse 1 over 10, we get 0.1, which is the initial concentration there. And then once you have that initial concentration, you can find the concentration over 10 seconds, and then we can do the first 3 half-lives next. So here's the half-life equation for second order. We know the initial concentration from a previous question, and we know the K value from the previous question. So it's 10 times 0.1. 10 is K, 0.1 is the initial concentration. So we get 1/1, which is just 1. So this is 1 second. So the half-life is each second. We go to and glance at the original graph up here that kind of matches every second. Every second, it looks like the concentration is halved. We get from here to here, here to here, here to here. Every second, it is being reduced by about a half. So for what are the first three half-lives? Well, we have 0.1 molar at, here's the concentration of A, here's our time at 0 seconds. So at 1 second, that's 0.5. At 2 seconds, that's 0.25. And at 3 seconds, that should be 0.125 molar. So those are the first three half-lives right there. And we can also do this off of a percentage base. So first half-life, you have 50% remaining. Second half-life, you have 25% remaining. Third half-life, you have 12.5% remaining of the original value. For questions 49 and 50, a quick reminder about what it means to be 45% complete. It means that 55% of the concentration is remaining. So whatever you have of the original concentration, the concentration after some point in time is going to be 55% of the initial concentration. Just to do a part equals percent times a whole thing, just to compare that to a general percentage calculation sample. And for 57, the big thing about pseudo order kinetics is we're making an assumption. If you look at these initial concentrations of V versus AV, the initial concentrations are vastly different. We're going to look at this of just V, and this is very, very large, very, very large compared to AV. This is very, very small. So if we do a little bar graph of initial concentration, we have AV initial versus just V initial, and we're trying to mark initial concentrations. AV is very small and V is extremely large. So if all of the AV reacts, there's a pretty much insignificant amount of V consumed. So practically 0 V is consumed, or I'll round off, so essentially remains unchanged, or concentration is constant. So the concentration of V is constant throughout this whole reaction. So what we're doing here is we are essentially combining the value of our K with the concentration of V. So the concentration of V is relatively unchanged. And so this K value, we're combining it together. So KV is going to give us this pseudo rate constant, and it's adjustment for this concentration of V that is really insignificant. So when it says, when we plot the AVs versus time, now AV is the one that matters, AV is the one that's changing. A plot of this versus time gives us a straight line. This slope is actually our pseudo rate constant over there. So let me get rid of all this bar graph stuff. So it's an assumption that we're making. So we're pretty much only focusing the reaction on the change in AV over time. So we have this change of AV over time, or the natural log of AV over time. We get this slope. And we normally say this slope is K. But because our rate law equation is making an adjustment, so we're just focusing on AV, this pseudo first order, this K prime, is essentially combining the concentration, the initial concentration of V into the original rate constant. So we're actually solving for the original rate constant, whereas the slope gives us this pseudo rate constant that goes there. So let's go ahead and do a little substitution and hopefully clarify that part a little bit. So the slope, the negative of the slope is going to be our adjusted rate constant, which in this case is negative. I'm just going to make that positive 0.32 per seconds. And then we need to account for the fact that the initial concentration of V is so large. So the actual K, to rearrange this equation, is K prime over the initial concentration of V, which is 0.32 over the initial concentration, which is 0.2. And this is going to get us our new K value. Now, K prime has the units of per seconds, and the concentration is molarity. So we're just going to adjust the units slightly, and we'll get our answer right now. (1.6). Molarity was a denominator, so we got to bring that up and give it a -1. So 1.6 is the actual rate constant, whereas the slope gave us K prime for the adjusted rate law. And the big hint for when you need to do this is when you look at the initial concentrations and there's one value that is vastly larger than the other, so it's going to remain constant. It's pretty much not going to change based on any sort of reaction with the other substance. Assuming it's a 1-to-1 reaction, there's nothing crazy. Even if it was like a 1 to 10 reaction, it really wouldn't matter. The difference in concentration is so significant that we are just going to blend these two together to get us an adjusted rate law that we're going to use to graph. That's it for now. Let me know what questions you have, and I will see you tomorrow in class.